You are listening to The Vocal Technologist. Spoken tech for your ears.
So the bit rattling around my head is this. You don't need the biggest, most expensive AI model to get the best result.
Yeah, it is completely counterintuitive, isn't it? I mean, we are constantly fed this idea by the industry that raw scale solves everything, Just throw a trillion parameters at a problem, buy a warehouse full of GPUs, and it will magically sort itself out.
Exactly. And I reckon that assumption is starting to crack under its own weight. So, as we always do here on Vocal Technologist, I want us to take a proper look at the quiet infrastructure shifts happening right behind all this AI hype. Because what the data engineering world is proving right now is that throwing raw compute at a problem is actually a bit ordinary.
Ah, it really is. The real magic is orchestration, right? It is context, and it is fixing the basic plumbing that gets you the actual wins. The assumption that scaling up is always the answer is just getting heavily challenged by the people actually building these systems for production.
Right. I mean, if you look at what the team at Cursor did to improve their AI coding output, they didn't just plug in a single massive frontier model from one of the big labs and call it a day.
No, they completely changed the structure. They moved to an agent swarm architecture.
An agent swarm, which sounds incredibly cool, like something out of a sci-fi film. But for you listening, if you are just trying to get your head around deploying AI in your own business, how does a swarm actually work in practice?
Well, instead of asking one giant, expensive model to do everything from planning to writing to checking, they split the workload. They use the expensive, highly capable frontier models strictly as planners. Think of these as the managers.
Right, so they do the high-level reasoning and set the strategy.
Exactly. They figure out the architecture of the code. But then they hand the actual execution, the grunt work of writing the lines of code off to a swarm of much cheaper, smaller worker models.
I love that. Here is the analogy that helped it click for me. It is like a master architect handing off blueprints to a team of affordable bricklayers. You wouldn't pay the master architect an exorbitant hourly rate to go out into the hot sun and lay every single brick themselves. You pay them for the genius of the plan.
Spot on. And you pay the crew for the fast, efficient execution. But, of course, if you have 20 bricklayers working at once, they might build walls that don't connect.
Yeah, that sounds like a nightmare.
It can be. So to keep it all from falling apart, Cursor uses shared design documents, layered reviews, and automated conflict resolution.
Wait, I have to push back there. How does an AI automatically resolve a conflict? I mean, if two cheap worker models write code that clashes, how do they fix it without a human stepping in?
It all comes down to that shared design document. That document acts as an immutable source of truth. When the system detects a merge conflict, say two models trying to change the same variable, it doesn't just guess.
So what does it do?
It prompts a specific reviewer agent to look at the conflicting code, compare it against the original master plan written by the frontier model, and rewrite the section so it aligns. The agents actually maintain the context themselves to prevent coordination failures.
That is fascinating. And does it actually yield a better product?
Oh, the results are wild. Cursor used this exact system to rebuild the entire SQLite database engine just from its documentation.
What, really? The whole thing?
Yeah, and they achieved the exact same or better quality compared to using a giant model for everything. But they did it with far less code generated, significantly fewer bugs, and at a dramatically lower cost.
Which completely proves that strong specifications and careful routing matter infinitely more than raw model size.
Exactly. But you can't just unleash a swarm of cheap models, hand them a design doc, and blindly trust the output. There is a catch.
Right, because if you are building enterprise software, one hallucination could take down the whole platform. What is the catch?
The catch is evaluation. To make an agent swarm work, you need incredibly strict, rigorous evaluation pipelines. You can't just vibe check the output and say, yeah, it looks about right.
Right. I assume you need something more systematic.
You do. Take Airbnb's approach to generative AI. Before they even attempt to build automated evaluations, they take 100 prototype outputs and review them entirely manually.
You mean just reading through them by hand, one by one, to see where the model hallucinates or breaks down?
Yep, exactly. And the reason they do that is because AI failure modes are weird. They don't fail like traditional software.
Because traditional software just crashes, right?
Exactly. AI software confidently gives you a beautifully formatted, completely fictional answer. So Airbnb manually looks for these real practical failure modes. Once they understand how the system actually fails in the real world, they build programmatic checks and calibrated LLM judges.
Oh, wow. So they use an AI to judge the AI.
Yes, but a highly calibrated one. And these automated judges are hitting agreement rates in the high 80% range when compared to human reviewers.
That is impressive.
It is. And what is crucial here is that they aren't just checking the final answer at the end of the pipeline. They are assessing the agentic systems across every single tool call, every reasoning step, and then the final output. If a worker model takes a wrong step early on, the judge catches it before it becomes a massive error.
Which brings us to the part nobody is really talking about. Because even if you evaluate the reasoning perfectly and you have this beautiful swarm of agents, they still have a massive blind spot.
Right, the context bottleneck.
Exactly. They are incredibly fast, they are logically sound, but they don't actually know how your specific business works. Stack Overflow put out a fascinating piece pointing out that context engineering is the actual bottleneck slowing down AI adoption right now.
Yeah, you see this all the time. An LLM can write a brilliant SQL query, but for it to do that in your company, a human has to manually gather the database threads, connect the internal tools, suss out the permissions, and validate everything.
Yeah, the setup time ends up taking you longer than the time you supposedly save by using the AI.
Yeah.
This is a bit dodgy.
The team at MotherDuck highlighted this exact same issue. They noted that without a dedicated context layer 1 that explicitly captures your unique business definitions, your edge cases, your institutional knowledge, well, these agents are literally just guessing when they interpret your company data.
Right, so they might write syntactically perfect Python code that is factually completely wrong for your specific database schema.
Because they don't know that your company defines an active user differently than the rest of the industry, yeah.
I am going to push back here, though. I am a bit skeptical of the terminology. Isn't a context layer just a fancy, dodgy way of saying documentation? Are we just rebranding company wikis to sell more enterprise software?
It's of a fair question, but it is much more active than a wiki. Think of it as executable documentation.
Executable how?
Well, the open source data tool DLTub calls this concept composable canonicals. Instead of just writing a text file and hoping the AI reads it and understands it, you encode your domain knowledge into versioned models.
Okay, so what does a versioned model look like in plain English?
It is code that defines your business rules. The source layers define the hard data transformations and the ontology, the exact definitions of what things are, and then the business layers merge identities across your different systems.
Oh, I get it. So if a customer is called a client in Salesforce and a user in your billing app, the model explicitly links them.
Exactly. So the AI agents use these stable concepts and identity rules as their playground rather than just being pointed at raw, messy data tables and told to figure it out.
That is brilliant because it bridges that massive gap between the data engineers who want strict control and the AI developers who just want things to move fast.
Yeah, LangChain is doing this right now with their new agent-first data stack, where they combine Hex and dbt. They encode the semantic models, the trusted data sets, and the execution traces directly into the stack itself.
So when an agent decides to generate a query, it is using reliable, governed business logic. It isn't guessing.
Spot on. The data team maintains total control over the modeling, and the agent gets a clean, perfectly reliable environment to work in.
I love that. And hey, if you are keen to keep untangling these kinds of massive architectural shifts with us, make sure you turn on notifications for the show. Because here's the reality. Feeding all that pristine context into an agent requires a staggering amount of data moving very, very fast.
Handling that fire hose of data is a completely different engineering challenge, and it is where a lot of companies are falling over right now.
For sure.
To give you an idea of the sheer scale required to feed these modern systems, look at Atlassian. They had to transition their internal event streaming platform called StreamHub from Amazon Kinesis over to Kafka on AWS managed streaming.
And the reason for the jump.
They were scaling from 22 billion to 145 billion daily events.
145 billion events a day. Just let that sit in your head for a second. That is an absurd amount of traffic. If you are a network engineer, hearing that number probably makes your eye twitch.
It tests every single part of your infrastructure. At that scale, everything breaks. They were hitting massive limits across their message brokers, their S3 storage limits, and even throttling the cloud provider's own control planes.
So how do you even begin to manage that without your cloud bill bankrupting the company?
Well, they found that implementing tiered storage helped cut costs significantly.
Basically moving older, less frequently accessed data off the expensive fast storage and onto cheaper, slower storage, right?
Yeah, exactly. But even with that, they had to rely heavily on strict quotas for their internal teams, incredibly aggressive data sharding, maintaining a lot of spare capacity for traffic spikes, and building bulletproof failover mechanisms just to keep the system from collapsing under its own weight.
Right. And this brings us perfectly to where the marketing hype hits an absolute brick wall. We hear heaps about vector search and how it is the magic bullet that solves all our AI memory problems.
Oh, definitely. You just convert all your company's documents into vectors, store them in a database, and the AI has a perfect recall.
Exactly. But nobody talks about the infrastructure bill until it arrives at the end of the month.
Let's unpack this for a second because the cost wall for vector search is very real, and it is catching a lot of engineering teams completely off guard. When you are operating at the 100 million to billion scale for vector indexes, the standard approach that everyone starts with completely breaks down.
Because the standard approach relies on keeping everything in RAM, right?
Yes. The industry standard right now is using in-memory approximate nearest neighbor indexes, often called HNSW.
Okay, let's demystify HNSW for you listening. What is it, and why is it so hungry for memory?
So HNSW stands for Hierarchical Navigable Small World. Think of it as a massive multi-layered web that connects similar concepts together. If you want to find documents similar to a financial report, it navigates this web incredibly fast.
But to traverse that web at millisecond speeds, the entire map has to live in active memory, in the RAM of your servers.
Yes, and it delivers incredible low latency performance. But at a billion vectors, keeping all those connections in RAM is financially ruinous.
Because RAM is vastly more expensive than disk storage.
Exactly. You bottleneck completely on memory costs before you even hit compute limits.
So how do you fix it? You can't just turn off the servers and tell the AI to forget everything.
No, you can't. The industry is shifting heavily toward disk-based options to solve this. Technologies like SPAN and DISCAN.
And how do those work differently?
Instead of forcing the entire web to live in expensive RAM, you shift the bulk of the index data onto solid-state drives, or SSDs, which are much, much cheaper.
But isn't reading from a disk usually a lot slower?
It is, but the trick is that these algorithms are highly optimized for sequential disk I/O. They group the data intelligently so that when the system needs to read from the disk, it grabs a whole chunk of relevant information at once.
Rather than hunting and pecking randomly across the drive, which is what normally causes that slowdown.
Right, so you are basically trading raw speed for cache.
That makes sense?
For large retrieval augmented generation, semantic search, or those agentic memory workloads we talked about earlier, you accept a higher, more variable latency. The search might take 50 milliseconds instead of 5 milliseconds.
But in exchange, you get a dramatically lower infrastructure spend. It is the necessary compromise to make these massive AI systems viable at scale without burning through your entire engineering budget.
Oh, absolutely.
Okay, well, while we are sussing out infrastructure costs and data movement, we absolutely have to talk about zero copy. If you work in data, you see this term everywhere right now.
Oh, the zero copy illusion. Vendors promise that we can query our data across completely different platforms without ever moving it or duplicating it.
But honestly, looking at the technical reality, it feels like we are having a lend. Half the time I look at a so-called zero-copy solution, it is definitely still copying the data behind the scenes.
It is an incredibly overloaded marketing term right now. There is a great breakdown on the Iceberg Lakehouse blog that points out zero copy actually covers 6 entirely distinct data architecture patterns.
Like federated query, format virtualization, storage mirroring, things like that.
Yes, catalog federation, and a few others.
Right, and how many of those 6 patterns actually avoid copying the data?
Only 3. 3 of the 6 patterns explicitly still create copies of the data. They just hide the process from the end user.
That is just false advertising. I mean, if it copies the data, it is not zero copy. Take federated query, for example.
Exactly. If I query a database in London from a server in Sydney, I might not be saving a permanent copy in Sydney, but I am still pulling all that data over the network wire every single time I run the query.
It is definitely misleading. And the hidden costs of those fake zero-copy setups are severe.
Even when you aren't strictly duplicating the permanent storage, you are paying massive fees for data egress out of your cloud provider.
Yeah, and you are hitting the source systems with repeated scan loads, which slows down the original database.
Plus, you have to constantly fight data freshness and governance issues because the data is in transit so often.
But there are places where the zero-copy concept actually works, right? Where we get the benefit of querying in place without the dodgy hidden costs.
There are. A massive win for this space is graph data. Graph databases are incredible for finding complex relationships, like fraud rings or supply chain bottlenecks.
But historically, you had to duplicate all your data out of your data warehouse and into a separate graph database to do it.
Exactly. Now, Neo4j's virtual graph is changing that. They push deterministic Cipher to SQL queries down directly to data warehouses, like Snowflake or BigQuery.
So Cipher being the language used to query graphs, and SQL being what the data warehouse uses. So instead of sucking petabytes of data out of the warehouse to build a standalone graph, it translates the graph question into SQL and runs it right where the data already lives.
Precisely. The compute happens on the warehouse side, and only the final answer comes back.
That is really clever.
It is. It allows data teams to do graph retrieval augmented generation and heavy batch enrichment against their governed, secure source data without duplicating it. Now, it doesn't replace a native graph database if you need millisecond latency for real-time credit card fraud detection.
Right. But for analyst exploration and feeding rich context to AI agents, it is highly effective and actually fulfills the zero-copy promise.
To be fair to the other side of this argument, the pure data engineering side of the house is pulling off some absolute magic right now.
Yeah, they aren't just whining about the costs of AI. They are fundamentally rebuilding the plumbing to make this massive scale possible.
The underlying storage optimizations happening right now are phenomenal. Take the work being done at a major music streaming service to index their massive data lakes.
Right.
They built an external index that maps search keys directly to file offsets and row numbers inside completely unmodified Parquet files.
Okay, hold on. Let's untangle that for anyone who isn't deep in data engineering. What makes a Parquet file special, and why is this hard?
So, a Parquet file is a columnar storage format. Imagine a massive spreadsheet. A normal database reads row by row, great for finding a specific user's profile.
But Parquet reads column by column.
Exactly. It is incredibly efficient if you want to find the average age of 1 billion users, but it is traditionally terrible if you just want to find one specific user's data because you usually have to scan massive chunks of the file to find them. They're built for huge, slow batch processing.
So how did this streaming platform make them fast without changing the files themselves?
By building this highly intelligent external index, they replaced long distributed SQL scan chains with parallel targeted ranged reads. And the real secret sauce is that they use write-time optimizations like per-key page flushing and ZSTD frame resets.
I'm definitely going to need you to pick apart ZSTD frame resets into plain English.
Right, sorry. ZSTD is a data compression algorithm. Usually Parquet files are heavily compressed to save space. If you want a piece of data in the middle of a gigabyte file, you often have to decompress the whole thing from the start to get to it, which takes immense compute power.
But a frame reset forces the compression tool to create distinct, independent blocks of compressed data.
Ah, you got it. So you don't
Okay.
have to unzip the whole file. The external index says the user data you want is in block 47. The system jumps straight to block 47, decompresses only that tiny chunk, and grabs the row.
I love that. Here's the library analogy again. Imagine a massive library filled with millions of encyclopedias. Usually, if you want a specific fact, you have to speed read entire shelves of books until you find it, which takes forever and costs a fortune in compute.
Right.
What the streaming service did is build a MasterCard catalog outside the library. When you want a fact, you check the catalog, and it points you to the exact book, the exact page, and the exact paragraph. You walk straight to it.
That is a great way to put it. That is exactly what they built. And because of it, they can now serve heavy, slow batch analytics and lightning fast interactive point queries from the exact same petabyte scale files. You get the cheap storage of a data lake with the speed of a transactional database.
That is brilliant. And, looking at all this, it isn't just new storage formats saving the day. We are seeing incredibly old, battle-tested technology being taught new tricks to handle modern AI scale.
Definitely. Look at Postgres. The listen and notify functions in Postgres, which act as a simple pub-sub system to let different parts of an application talk to each other, well, they have been around forever.
But they typically bottleneck and crash if you push them too hard.
Exactly. A company called DBOS managed to scale Postgres PubSub from 2,900 writes per second all the way up to 60,000 writes per second.
How on earth do you squeeze a 20x performance increase out of standard Postgres? Did they rewrite the database?
No, they just changed how they use it. The bottleneck usually happens because systems treat the notify calls as the absolute source of truth, creating massive disk I/O and network chatter. Instead, DBOS uses them simply as lightweight wake-up signals.
I see. So they buffer the calls, batch them together, and use occasional polling as a safety net. So instead of the database screaming for attention every single time a single row changes, it calmly hands over a batch of updates all at once.
Yes. It keeps the latency down to around 15 to 100 milliseconds while handling massive enterprise-grade throughput. It is amazing how much headroom is left in systems we thought were maxed out a decade ago.
Yeah, Zalando proved the exact same thing. They had a homegrown Advent join system that was more than 7 years old, and it was struggling to keep up.
Oh, right, the Flink migration?
Exactly. They migrated the entire thing over to Apache Flink. Now, they're processing 200 megabytes of data every single second, storing unmatched events in memory until their counterparts arrive, and checkpointing the progress every 3 minutes to disk so they never lose data in a crash.
And the business result of fixing that plumbing, they cut their daily EC2 cloud compute costs by more than half, and they actually improved their event matching accuracy. It is a perfect example of how mature, rigorous data engineering practices drive massive efficiency.
Stepping back from all this, it really feels like everything old is new again. 2 years ago, we thought generative AI was going to completely throw out the engineering playbook. We thought it was magic.
Yeah, but we are just running into the exact same walls we hit with web-scale data 20 years ago. It is still about compute, memory, and routing.
Exactly.
Stephanie Wang, a brilliant engineer in this space, summarized this perfectly. She pointed out that AI isn't replacing databases at all. Instead, AI is slowly relearning everything databases already knew about strict cost control, managing memory hierarchies, and dynamic routing. The infrastructure underneath these autonomous agents has to be just as rigorous, if not more so, than the infrastructure running a traditional financial database.
That is so true. We spend so much time in the media hand-wringing about open source models being dangerous or worrying about rogue AIs on the internet. But as the developer Anti-Res pointed out, the real risk of a catastrophic AI incident comes from inside the frontier labs themselves.
Right. It comes from insider leaks of these highly integrated, massively proprietary systems.
Exactly. If we are going to build these incredibly powerful automated systems that touch every single part of a business, we need to make absolutely sure the foundation isn't dodgy. Vocal Technologists, see you soon.
Spoken Tech for your ears.